What's up, folks? This is Ref Bari, Brown University physics graduate student. Today, I'm bringing to you the next lecture of advanced quantum mechanics. Now, today we're talking about one of the coolest things ever in physics, and that is how light moves from point A to point B. That's going to be critical for our fundamentals of quantum field theory. It's going to establish the foundations of calculus of variations, which we will then use to combine special relativity with quantum mechanics. So let's hit it. The first thing I'm going to ask you is something very simple. How does light move from air to water? Now, this is a high school physics question, but it has deep implications for quantum field theory. So let me draw the situation. Here, for example, is a glass of water. In this glass of water, there is, huzzah, water. And we have a beam of light coming in to this glass of water. Now, the beam of light, as you can see, is coming in at a pretty steep angle. And now I'm going to draw the normal. And as I draw the normal, you'll see, let me change the angle that the light comes in. Let's make it steep like this. So the light is going to slow down in the water, and so the angle of refraction is going to be greater than the angle of incidence, as shown there. So if you want to calculate the exact values of theta I and theta r, given the indices of refraction, we'll simply use Snell's law. N1 sine theta 1 equals N2 sine theta 2. Now, this is all good and fine. Every high school physics student learns this, but the question is why? Why does light take that specific path? In other words, why does the beam of light not refract this way? After all, that path also has the same endpoints. It starts at the same point and ends at the same point. It just takes a different path. Or why doesn't the beam of light take this path or this path? Okay, what is so special about the specific path that the beam of light chooses to take by obeying Snell's law? Why is Snell's law so special, in other words? Now, this is not a question that is obvious to ask. To even ask that question is kind of strange. You must have an ulterior motive in asking that question. But that question becomes more natural to ask if we phrase this picture in a phase diagram. So not in a phase diagram, but rather in a phase space. So here's what I mean. If I plot space, so on the y-axis I have space, and on the x-axis I have time. If I plot space versus time as follows, and I say that this point A is my starting point, point B is my ending point for the light beam. So let's say that pictorially, the beam of light takes this path, okay? Let's say, just for illustration purposes, that that is the path of the beam of light. Now, the question we ask right now is, why doesn't the beam of light take this path, or this path, or this path? It is very strange for the beam of light to opt for this one specific path described by Snell's law. To answer this question, we had Pierre de Fermat, who came along in the 1700s or 1600s and proposed that light follows this special trajectory because that is the trajectory which minimizes the time. Okay, what does that mean? That means, for example, let's say you have something like this, where you have air, glass, and then air once again. So let's say you basically have a glass plate and you shine, let me draw the normal lines. Let's say you shine a beam of light onto this glass plate. Well, light is of course going to slow down in the glass plate, and it's going to merge over here, and it's going to merge at the same angle that it came in fact. Now the question is, why does the beam of light pursue this path? Why does it not take a different trajectory? So for example, why doesn't the beam of light take this trajectory or that trajectory? Right? There are an infinite number of possibilities for the number of trajectories the beam of light could take. What is so special about this trajectory given by Snell's law? Okay, we're just asking the same question we did before. Why is the beam of light choosing to go this specific path? And what Fermat proposed was that light takes the path that it takes because that is the path of least time. Let me say that again because it is worth emphasizing. Out of all the possible paths that the beam of light can take, it takes the one it takes because that is the path of least time. So for example, let me draw a picture here. Hopefully folks can see what's down here. Let's say that this is the starting point for a beam of light and this is the ending point. And let's say that the beam of light pursues this trajectory. We'll call this trajectory optimal, okay? This is T sub O, the optimal trajectory. The optimal trajectory is the trajectory that takes the least amount of time for the light beam. So maybe that is, let me just make up a number, 6 seconds. Now, if the beam of light had traveled any other path between the 2 points, those paths would have taken more time. For example, this second trajectory, T sub 1, may have taken 7 seconds. This third trajectory might take 8 seconds. This fourth trajectory may take 9 seconds, so on and so forth. No matter what other trajectory you draw, all of them will be greater than the optimal trajectory of 6 seconds. So the reason why light obeys Snell's law is so that it can get from point A to point B in the least amount of time. Now the next question you can ask is one level deeper. Why is light in such a hurry to get from point A to point B? Why is light even caring about the amount of time it takes to get from point A to point B? Light doesn't have chores to do or a job to go to or a business to attend to. Why does light care about time? To answer that question, we need quantum field theory. And today, we're going to start the first part of the answer to that question by trying to understand calculus of variations. So the first thing I'm going to do is write down this problem from an energy perspective, okay? We're going to write down the kinetic energy of the beam of light, the potential energy, combine them in a conservation of energy statement, and then try to figure out how the kinetic and potential energies of the beam of light vary as we move to a different trajectory, okay? That's a big picture of what we're going to do right now. So let's do it. First of all, the kinetic energy is pretty simple. We write it as the average kinetic energy, at least, is 1 over tau, where tau is the total time. The integral from 0 to tau of 1/2 m x dot, which is a function of time, squared dt, right? So there you go. That's the average kinetic energy of the photon or whatever system we have over the entire time. And the average potential energy is very similar. It's just something like this, where x is also a function of time. All right, and our total energy is just the sum of these, and it is always conserved. So now what we want to do is figure out what is the change in our kinetic energy and potential energy as we perturb the trajectory of the photon by a little bit. What do I mean by that? Let's draw a picture. So here, for example, is another space-time diagram. Okay, this is space on the y-axis and time on the x-axis. And let's say that this is the true path between 2 different points. Maybe this is the true path followed by the beam of light. Now, let's call this true path f of x. What if we deviate from this true path by an amount epsilon? And that gives us another path. And this path, this second path, I'll call it f of x plus epsilon times delta x minus x naught. Now, this looks strange. This looks maybe foreign, but all I'm doing is I'm increasing that deviation by a little bit, epsilon, okay? I'm just deviating from the true path by a small amount, epsilon. That's all I'm doing. That's all that's happening here. So this right here is what we're trying to do. We're trying to figure out if we deviate from the true path of the beam of light, then how much will the kinetic energy and the potential energy of the photon or whatever particle change? So to address this question, the first thing we need to understand is something called functionals from calculus of variations. So let's do that. Let's try to understand functionals. What is a functional? Well, hopefully you know what a function is, because otherwise you wouldn't be taking QFT. A function is simply a box. It's a machine which takes in a real number as an input, so some input x, and spits out another real number. That's all a function is. A functional is an upgraded version of a function. It's a function of a function. And so the input of a functional is a function, but the output is still a real number. Now this is very abstract when you first hear about it, so it's worth going through some examples. So let's hit it with some examples. So for example, let me draw a straight line here. One simple example of a functional is an integral. So for instance, let's say we have the functional of f of x is defined as the integral of f of x dx from -1 to 1. This is a functional because whatever function I provide to this integral, it's going to spit it out in the integral and evaluate it. It's a definite integral, right? So let's say that f of x is x squared. So f of x is x squared. So if f of x is x squared, then I simply have the integral from -1 to 1, x squared dx, which is x cubed over 3, which is some number. I don't really care. That's not the point. The point is to show that this is indeed a scalar once we plug in a function into the functional. Let me show another example of a functional just for sake of pedagogical purposes. Another example of a functional could be some kind of a scalar, 5 times the functional times the function squared dx from, let's say, 0 to 3. Okay, just making up arbitrary functionals. And let's say our function f of x, our input function is, let's make it something like x cubed. So then we'll have 5x cubed squared, which is x to the 6th, dx from 0 to 3, and then you'll get some kind of a definite output from that integral. Now, you can even consider a function, a regular function such as f of x, as a kind of version of a functional. How so? Well, let's say you have a function f of x. You could write it as the integral of f of y times delta y minus x dx. And so if you evaluate this integral, this will simply give you f of x, right? So a function, even a regular function such as f of x, can be kind of thought of as a very basic functional. So now that we've talked a little bit about functionals and explained where they come from, let's talk a little bit about differentiating functionals. What do I mean by differentiating functionals? Well, if you have a regular function, for example, x squared, we all know how to take the derivative of x squared, right? Just use the power rule. This is going to give you 2x. But what is happening graphically? Let's just go back to the limit definition of the derivative. Graphically, what's happening as you take the derivative of a function is you're drawing the tangent line to that function. So let's say you have a picture as follows. Okay, so we are considering 2 points along our function x and a closed value x plus h, and 2 outputs f of x and f of x plus h, which correspond to our 2 inputs. And so if we draw a line connecting our 2 points along the function, it won't give us a line that's tangent. No, it'll give us a line that is secant to our function. But as we close this divide between x and x plus h, in other words, as h approaches 0, our secant line will slowly approach our tangent line and therefore deliver the true derivative of the function. And we can apply this same idea to a functional. But first, let me remind you of the definition. The limit definition of a derivative is that f prime of x is the limit as h approaches 0 of f of x plus h minus f of x divided by h. This is simply the limit definition of a derivative. Now we can apply this exact same definition to a functional, right? Because the basic principle stays the same. We're just now dealing with inputs that are now functions instead of real number inputs. So how does this generalize for a functional? Well, we're now going to have, instead of df dx, f prime of x was simply another way to write df dx. For a functional, we use the notation delta f delta x, okay? Or actually, we're not finding the change in a function with respect to some input scalar. No, no, no. We're trying to figure out, in fact, this is incorrect. We have to upgrade our notation even further. This has to be delta capital F, where f is our functional, delta lowercase f of x. So this is saying I want to figure out how much my functional changes with respect to a specific function, okay? So that specific function could be x squared, x cubed, sine of x, whatever you choose. So this is equal to, all right, folks, so it seems like my mic got cut off last time. So let's go through this one more time. So the derivative for a functional derivative, delta f of x is written as follows, right? We're finding the change in our functional as we make a small change in the function input, not in a real number input. So that is the limit as epsilon. Epsilon, remember, is our deviation from the true path. So for example, if our true path from A to B is this path right here, epsilon is this deviation from the true path to this fake path underneath, right? And then we are evaluating our functional at that fake path and then subtracting our functional evaluated at f of x. So we're evaluating the difference between our functional evaluated at the true path and at the fake path, and then decreasing that distance. So another way we can understand that is with this kind of a diagrammatic picture right here. Imagine that this outline right here is an infinite dimensional vector space where the functional lives. And here, this point right here represents a function, f of x. And that function, if we take that function is the true minimum of our functional. If we take a small step in a random arbitrary direction with a step size epsilon, then we'll arrive at this new function, f of x plus epsilon times delta x, and this will no longer be the true minimum. This is now a new function that does not give the minimum when inputted into the functional. So the question is, okay, big deal. Now, how does this give us the derivative of our functional? Well, as we decrease this step size epsilon to 0, we approach the derivative of our functional. Another way to imagine that is with this phase diagram picture right here. This phase space picture shows the path of least time between points A and B, f of x, and a small deviation, epsilon, from the true path that gives us this fake path, f of x plus epsilon times delta of x. So now let's take a look at a couple of examples dealing with functional derivatives. So let's start with a basic example. Consider the functional I of f of x is equal to the integral from -1 to 1 of f of x dx. So this is our first example, and it's pretty basic. We just have an integral for our functional. Now, the question is, what is the functional derivative of this functional? Well, recall that the definition for the derivative of a functional, delta I delta f of x, is given by the limit as the deviation from the true path approaches 0 of our functional evaluated at the fake path, f of x plus epsilon times delta x minus x naught, minus our functional evaluated at the true path, all divided by epsilon. And so now all we have to do is plug our known values in here. So we have delta I, delta f of x is equal to the limit as epsilon approaches 0. Now, what is the functional evaluated at the fake path? Well, that's going to be the integral from -1 to 1 of f of x plus epsilon delta x minus x naught dx minus the integral of f of x from -1 to 1 of dx, all divided by epsilon. Alrighty, so over here we notice that f of x and f of x cancel out. And so we are left with delta I delta f of x is equal to the limit as epsilon approaches 0 of, well, epsilon and epsilon also cancel out, so the limit goes to hell. And so we're just left with this Kronecker delta of x minus x naught dx. Remember that there's still an integral from -1 to 1. And so what is this? What is the integral of delta x minus x naught dx from -1 to 1? Well, it depends on what x naught is, right? If x naught is between -1 and 1, then this right here, -1 and 1, then this integral right here will evaluate to 1. Otherwise, it will evaluate to 0, as we have written over here. So that is the functional derivative of this simple integral. Let's consider now a more advanced problem. So for our next problem, we have the functional j of f is given to be the integral of f of y to the pth power times phi of y dy. And this is an indefinite integral, and we are asked to compute the functional derivative of this. Now this one is going to be a bit tough, but we'll be able to handle it. So the first thing I'm going to do is once again write the definition of the functional derivative for this, delta j delta f of x. Now look over here and you'll see that j is a function of y, but we're evaluating the functional derivative in terms of x. In fact, one important thing to note is that this functional derivative, delta f of y with respect to delta f of x, is equal to the Kronecker delta of y minus x. And this should be sensible because remember, delta x, for instance, is simply 1, and delta x is simply 0. So if you have delta x sub I with respect to the derivative with respect to delta x sub j, that'll simply be delta I comma j, right? Where xi and xj are different coordinates. So here it makes very much sense why delta of f of y with respect to delta of f of x is simply the Kronecker delta of y minus x. So here we're taking this function of y, evaluating the derivative with respect to f of x. So this is going to be the limit as epsilon approaches 0. And now we're going to evaluate this functional at the fake path. So the fake path is going to be f of y plus epsilon times delta y minus x, and then we're going to resolve this to the pth power times phi of p dy. Okay, so that's a massive integral right there, but that's that. And then we have the functional evaluated at the true path. So that's just going to be this component written up over here. So we're going to have f of y to the pth power times phi of y dy. So that's all we have for the functional evaluated at the true path, and then divide all of this by the size of my deviation. Now, if I look over here, I can make an approximation. This right here, f of y plus epsilon times the delta to the pth power is simply a binomial expansion. Okay? Remember, for example, x plus y squared is x squared plus 2xy plus y squared. This is something very similar. And so we can expand this out as follows. F of y plus epsilon times delta y minus x to the pth power is equal, or approximately equal, to f of y to the pth power plus p times all of this, okay, epsilon delta y minus x. And don't forget, we'll have this f of y, this term, to the p minus 1th power. And then we'll also have a second order term, for instance. This right here will be p choose 2, okay, it's just binomial expansion. So epsilon squared delta squared y minus x times f of y to the p minus 2, and so on and so forth. Okay, so now here's the thing though, epsilon is a pretty small number because we're taking the limit as epsilon approaches 0. So this right here will approach 0, and so this second term will die off, and so you'll only be left with this term, these two terms right here. And so if I go ahead and plug that in into my limit, what am I going to obtain? So let's write that down. Delta j delta f of x is going to equal what? Well, we're going to have these two terms, f of the integral of f of y to the pth power plus p epsilon delta y minus x times f of y to the p minus 1th power. And then, don't forget, we have a phi of y all the way over here and over here. By the way, this should be phi of y, not of p. Sorry if that typo screwed you up, but nonetheless, we'll continue. And I have minus f of y raised to the pth power. And remember, there's a phi of y all factored out from all of this. So phi of y, you probably won't be able to see if I write it there. So I'll put it here, phi of y dy. And all of this is to be divided by the size of my deviation. Now, of course, f of y to the p and f of y to the p cancel out. And we have epsilon and epsilon canceling out. And so what are we left with? Well, let me proceed to step back over here. Hopefully you can still see what I write. So delta j, hopefully you'll see what I write, delta j with respect to delta of f of x is equal to, okay, so my functional derivative right here is equal to the integral of p times delta y minus x times f of y to the p minus 1 times phi of y dy. Oh, that's it. That's all there is. And so if I integrate this with respect to y, well, then this delta function is going to make everything with respect to x. And plus, I'm integrating y out anyway. So this is going to be p times f of y to the p minus 1 times phi of x, because we integrated out x. And this should, in fact, be x as well. And so there you go, ladies and gentlemen. This is the functional derivative of our functional right there. And now we have one more example to consider. Our last example looks a little bit like the chain rule, not quite, but a little bit. So let me write it right here. So we have a functional called h of f, which is given by the integral of a function g, which is a function of f of x dx from a to b. G itself is a functional of f of x. So how do we compute the derivative here? Well, we're just going to follow the recipe outlined here. So I'm going to write delta h delta f of x, okay, is equal to what? Well, I'm going to have my functional evaluated at the fake path. So I'm going to have the integral from a to b of g of f of x plus epsilon times delta x minus x naught. Okay, that's the functional evaluated at the fake path minus the functional at the real path, right? So minus g of f of x all times dx. And now I'm going to divide all of this by the size of my deviation epsilon. Oh, of course, there's a limit here that does not go unsaid, but I simply forgot to write limit as epsilon approaches 0. And now take a look at what we can do. We can employ a basic Taylor approximation right here. What do I mean by that? Let me show that right here. Let's say you have a function f of x plus h, right? then a basic Taylor approximation will allow you to approximate this as f of x plus h times f prime of x. Okay, why is that? What's the justification behind that? Let me write more over here. So the justification behind that is actually just straight from Taylor series. Recall from Taylor series that f of x is approximately f of x naught plus, sorry, not f of x naught, yep, actually f of x naught, plus x minus x naught times f prime of x naught. Now if I replace x naught by x and x by x plus h, then I can write f of x plus h is approximately f of, instead of x naught, I'm going to replace that by x. So it's going to be f of x plus h minus x times f prime of x. Okay, so x and x cancel out, and so I'm left with this. And so in this case, my x is f of x, and my h is epsilon delta x minus x naught. So that's how I'm going to employ my approximation here. So let's employ the approximation right here. Let's erase all of this. Okay, so our integrals, our functional derivative is going to become delta h delta f of x is equal to the integral from a to b of what? Well, here we have g of f of x plus epsilon delta x minus x naught times g prime of f of x minus g of f of x because of this term. So minus g of f of x dx all divided by epsilon. So now, of course, this g of f of x and this g of f of x cancel out. So we're left with the integral from a to b of epsilon and epsilon cancel out. We have the delta of x minus x naught times g prime of f of x dx. And of course, this is simply going to evaluate to the Dirac delta function is going to pick out g prime of f of x naught in particular. And so this is the result of our functional derivative. So folks, thank you for watching this episode of Advanced Quantum Mechanics. We'll see you in the next one.